So the focus of the lesson for today is the rational root theorem. And this states, for every rational root, when the function is equal to 0, can be found by the form p over q, where p is a factor of the constant and q is a factor of the leading coefficient. So in this example, it says to find all the possible roots. Well, we're going to be using the rational root theorem then to do that. And you first need to identify your constant term. In this case, that's going to be 8. That is our p-value. And our leading coefficient is 3. That's our q-value. Remember, if your polynomial is in standard form, your leading coefficient will be the first coefficient, or the coefficient of the first term. So we are going to divide 8 by 3. But before we can go ahead and divide those, I want to write the factors of 8 and 3. Well, the factors of 8 are 1, 2, 4, and 8. And the factors of 3, well, 3 is prime, so it's just going to be 1 and 3. So if we have a 0 that occurs from this polynomial, that 0 will be in the list I'm going to write next. Alright, so what you do is you're going to take every number in the numerator and write it over every number in the denominator. Let's start with 1. So we're going to write 1 over 1, which is just 1. And that could be a positive 1, or we might have it as a negative 1. We don't know the sign of the 0. These are just going to give us the absolute value of those zeros. Now I want to write 1 over 3. Again, that could be positive and negative too. Positive or negative. Alright, now let's take the 2. We want to write 2 over 1, which is just 2. Again, the 2 could be positive or negative. And now the 2 over 3. And we continue this throughout all of the numerators, all the terms in the numerator. 4 over 1, which is 4, or 4 over 3. Then we do 8. 8 over 1, which we can reduce to just 8. And then 8 over 3. One way to rewrite this list, instead of writing plus or minus this number of times, is I could just write it plus or minus and use a brace. 1, 1/3, 2, 2/3, 4, 4/3, 8, and then 8/3. If there were any fractions in this list that could be reduced, you would want to make sure that you did that. In this case, our fractions are already in simplified terms. Okay, so again, what the rational root theorem is saying is that if I were to graph this polynomial, and if it had any real roots or any real x-intercepts or any real solutions, those solutions would all be in this list. Okay, let's put this to practice again. So example 2 says find the rational roots. 15x cubed minus 32x squared plus 3x plus 2 equals 0. Well, basically, if we want to find the rational roots, that's telling us to solve for x. What values could x be that polynomial would equal 0? So we have done these problems before, and we've always looked to factor them. I've got 4 terms here. Can I do factoring by grouping? In this case, factoring by grouping will not work. So that's where we're going to do the rational root theorem. And we got to start by listing all the possible roots. So I take my constant term, which is our 2, and I write it over my leading coefficient, 15. And again, I want to break down the factors of 2 and 15. Well, 2 is prime, so that's just going to be 1 and 2. Factors of 15 are 1, 3, 5, and 15. Oops, not 12. Okay, and now I'm going to take each number in the numerator and write it over each term in the denominator. And I'm just going to save myself time by writing the positive and negative sign in front of my braces. So we're going to start with 1. 1 over 1, 1. 1 over 3, 1/3. 1 over 5, we have 1/5. And 1 over 15, 1/15. And then I'm going to do the same thing to 2. 2 over 1, which is just 2. 2 over 3, we have 2/3. 2 over 5 is 2/5. And 2 over 15 is going to be 2 over 15. And now we're done with step 1. So step 2 then is once we have the list of possible zeros, or the list of where our x-intercepts possibly might be, we are going to test each one, or at least test until we find some that work. So I'm going to start with the integers first. We're going to test 1 and -1. So you could do this in your calculator. You could use this, and the calculator has a lot of different features. Maybe you want to use it in the table. Maybe you want to use it just on the home screen. If you are evaluating each one, you could plug it in simply for x, and doing this straight on the home screen, we could see what we get when we have x is equal to 1. And we see the answer would be -12. So remember, we're looking for 0, okay? You could also do this with synthetic division. Now let's check -1. From -1, we get -48. So we can see clearly that 1 and -1 do not work. I'm going to try 2. When I plug 2 into my function, I get 0. So I found one that works. I can continue from this whole list and try in each one, 1/3, 1/5, 1/15, all of those, and see if I can get all of the zeros. Remember, we have a cubic function here, so we are looking for 3 possible zeros, and we have now found one of the 3. All right, step 3. It says use that root that you found, and you're going to factor that polynomial using synthetic division. We know that 2 works. 2 is our root. Let me write down our polynomial function first. This is what we started off with, 15x cubed minus 32x squared plus 3x plus 2. All right, so we know 2 is a root because it works. When we evaluated it, we got a result of 0. So what we're doing here is we're not necessarily, I guess you could call it as a check with synthetic division. We know that if you do synthetic division with a root, that we should have a remainder of 0, which we've already done with the evaluation process. However, synthetic division allows us to factor this polynomial and break it down into something that hopefully we can factor the rest of the way and find our missing zeros. You know, we're looking for 3 approximately. We're hoping for 3 real zeros. We'll see if we get that. So let's do the synthetic division process. You want to take the coefficients of your polynomial. We do not need any placeholders. And we're going to drop your mama. So 15. 15 times 2 is 30. -32 plus 30 is -2. -2 times 2, -4. 3 plus -4 is -1. -1 times 2 is -2. And again, there's my remainder of 0, which I was already expecting. All right, so by dividing this polynomial by 2 with synthetic division, we now have a polynomial, or resulting polynomial, of 15x squared minus 2x minus 1. Okay, so our last step, step 4. Now we want to set those factors equal to 0 and to solve. We're going to solve to find the remaining roots. So remember, when we did synthetic division from step 3, whoops, let me erase that. When we did synthetic division from step 3, we found the resulting polynomial 15x squared minus 2x minus 1. All right, so that's a quadratic. You know, we might see if this factors, or you could look for the quadratic formula. But we're going to have to solve that equation right there. Solving this equation will get us our last two zeros. So it's your choice if you want to see if it's going to factor or do the quadratic formula. I'm just going to go ahead and go straight to the quadratic formula because I know that that's going to work every time. So we have x equals 2 plus or minus the square root of b squared minus 4ac all over 2a. The radicand is going to be 64. So we have 2 plus or minus the square root of 64 over 30, which reduces to 8. This is going to reduce or break down into 2 plus 8 over 30, and then 2 minus 8 over 30. So 10 over 30 is just 1/3. And this gives us negative 6 over 30, which is negative 1/5. So our last two zeros are 1/3, negative 1/5. And of course, we need to add in that very first zero we found of 2. So we have found all three zeros, and they were all real numbers. Okay, putting it all together, we're going to do one more example. So we want to find all the zeros of our function h of x is equal to 7x cubed minus x squared minus 21x plus 3. So step 1, we have to find our p over q list. So I have to take 3 over 7, and before I can write the list, I have to break down 3 and 7 into their factors. So the list is really going to be, first of all, plus or minus, brace, 1, 1 over 1, 1 over 7, 3 over 1, and 3 over 7. So we really only have 8 possible numbers to try. 4 of those being positive, 4 of them are negative. Step 2, find a number that works. I like to start with my integers. So I think the first thing I'm going to test is probably 1 and negative 1. When I plug in 1, I get negative 12. So that one clearly does not work. When I use negative 1, I'm getting 16. All right, let's try 3 and negative 3. And if you need to, hit pause so that you can get a chance to try them before I write down the answer. Okay, when I plug in 3, I have 120. Clearly does not work. Negative 3 gives me a negative 132. Now I'm going to try 1/7 and 3/7. When you try 1/7, be very careful with how you put it into your calculator. I have 1/7 is 0. Great. I just found my first one. Now I'm going to do synthetic division with 1/7. And it's perfectly fine to do synthetic division with a fraction. I do not need any placeholders, so I can just go ahead and take my coefficients, draw out my first term. 7 times 1/7 is 1, and I get 0. Negative 21 times 1/7 is negative 3. I did my math right. It works out. I get a remainder of 0, which is what I should have. This resulting polynomial is now 7x squared. It would be plus 0x, which we don't need to write, minus 21. I can continue with my list and find the other two, or I could go ahead and just solve this quadratic. This is an easy enough quadratic to solve algebraically because I do not have that b term. So I'm just going to go ahead and add 21 over. Divide by 7. And I square root. And I get x is equal to plus or minus square root of 3. The square root of 3 is not in our list because it's not a rational number. It's irrational. So we would have had to find the other two zeros algebraically, just like what we did. So putting it all together, our three zeros, or you might want to think of it as our three x-intercepts, are 1/7, positive square root of 3, and negative square root of 3. Okay, I'm going to leave you with your homework, but if you have any questions, please do not hesitate to reach out and ask.